Hey everyone, in this video we're going to learn how to identify exponential growth or exponential decay. More specifically, we want to be able to look at an exponential function and decide if it models growth or decay and what the growth or decay rate is. Now the best way to do that is build up to an exponential growth or decay function. Starting us off, a herd of deer has a population of 20. If the population grows by 35% in a year, what value can we multiply 20 by to get the total number of deer after 1 year? Okay, so we have exponential growth here. The population is growing by 35% in a year, and our initial population of deer is 20. Okay, so if we want to figure out how many deer there would be after 1 year, we'd start with the 20 that already are there, and then it grows by 35%. So we have to figure out what 35% of 20 is. So to do that, we take 20 and multiply it by 0.35, the decimal equivalent of 35%. Now we can evaluate this and get our answer, but the question said what value can we multiply 20 by? Well, this isn't 20 times a single value. This is 20 plus 20 times 0.35. But if we notice, both terms have 20 in them. So we can take out a greatest common factor of 20, and what would be left is 1 plus 0.35, which, combining the terms in the parentheses, is 20 times 1.35. So to answer the first question of what value can we multiply 20 by, we can multiply it by 1.35. Now, what would our answer to how many deer would there be? Well, we can go into our calculator. You can see I already typed it in. 20 times 1.35 is 27. So there are 27 deer after 1 year. Now let's talk for a second. Why is it 1.35? Right, some of you might have thought initially, well, just take 20, multiply it by 0.35, and you would get your answer. In that case, it would be 7. Well, first, the issue with that is it's not growing. Right? If we're going from 20 to 7, that's decaying, that's decreasing the population. But why 1.35? Well, if we think about this, how we set it up in that first line, we took the population that existed, which is 100% of the deer that are there, and we added 35% on. Well, what's 100% plus 35%? That would be 135%, which in decimal form would be 1.35. Right, so this percentage equivalent is 135%, which indicates we have the initial population plus 35% extra. So our goal by the end of this video is to identify that if we were given an expression like this, that we're growing by 35%. Okay, so just keep that in mind as we continue on. If the herd of deer continues to grow by 35% each year, how would we figure out the population of deer after 2 years? Okay, well, start with the 20 deer. To get after the first year, we multiply it by 1.35. We get the 27. Then we're going to take that and multiply by 1.35 again. Right, so we have repeated multiplication. We can condense this nicely as 20 times 1.35 to the second. Now some of you are probably wondering, why didn't I just do 27 times 1.35? And we could have. That would have answered this question. But remember, we're trying to build up to an exponential growth function here. So now, how would we figure out the population of deer after 3 years? Well, if we take the same line of thinking from above, we'd have 20 times 1.35 times 1.35 times 1.35, right, for the first, the second, and the third year, which we can condense nicely as 20 times 1.35 to the third. Okay, so we have repeated multiplication to figure out the population from year to year, which we can condense with an exponent. So what type of function could we use to model this population? Well, an exponential function, as we discussed earlier. Now write a function to model the number of deer after X years. So that means we'd be multiplying 20 by 1.35 X times. So we can write our function as 20 times 1.35 to the X. So the X indicates that we're multiplying 1.35 out X times, right? Repeated multiplication, which means we have an exponential function. So there we have our first exponential growth function. Growth rate was 35%, so we should see that part there. And then 1.35 because we're growing, 100% of our population plus the 35% extra. So let's generalize this. We can use the following function to help us model any quantity that grows or decays by a fixed percent at regular intervals. And we discussed this idea of regular intervals, right? Like 0, 1, 2, 3 weeks, not 0, 2, 8, 11, right? That wouldn't be regular intervals. So the equation is A equals P times 1 plus R to the T. So we have an exponential function. The variable T is in the exponent. 1 plus R, this is the base of the exponential function. Now, what does each individual variable represent? Well, A is the amount at time t, rather. Okay, so if we're looking for the deer population in 2 years, well, what the population is A. T is 2 years. P is the initial amount, so how many deer we started with. In that case, it was 20. R is the growth or decay rate per time interval. So in that first example, the population was growing at 35% each year. A positive R value indicates growth. A negative R value indicates decay. Right, so if we have 1 plus 0.2, we're growing by 20%. 1 minus 0.2, or 1 plus negative 0.2, that would be decaying at 20%. We're going down 20%. T is the number of time intervals that have passed. So in that first example, it was years, right? 2 years or 3 years. And 1 plus R is the factor, the common ratio, what we're multiplying from year to year, that you multiply by over each time interval. So again, over years. And this common ratio is what we define as the base of the exponential function that we're creating. Now, in the rest of this video, we're going to work on identifying this growth and decay rate. And in the next video, we're going to create this function on our own. Determine the percent growth or decay as well as the y-intercept for each of the following exponential functions. Our first function is y equals 12 times 1.1 to the x. So the base of the exponential function is defined as 1 plus r. So we have 1 plus r equals 1.1. If we solve for r, we can subtract 1 from both sides, so that would be r equals 0.1. Now remember, if we read carefully, we want to determine the percent growth or decay. So if r is 0.1, that means there is 10% growth. R is positive, that's why I know that there's growth, and 0.1 as a percentage is 10%. And even if we look back in the original exponential function, we're multiplying by a value larger than 1. Our numbers are going to get bigger, so that would be growth. The y-intercept, well, that's the point where x equals 0. So if we plug 0 in for x, 1.1 to the 0 is 1. 12 times 1 is 12. So 0, 12. And we can think of that as the initial amount. 12 would be the initial amount in this function. Next, we have y equals 5 times 0.81 to the x. Okay, so the base of the exponential function is 1 plus r, so 1 plus r equals 0.81. So if we subtract 1 from both sides, we get negative 0.19. So that means that we're decaying. We have exponential decay. 0.19 as a percent is 19% decay. And if we look back at the original exponential function, we're multiplying by a base value that's less than 1. Right? So our numbers are going to get smaller as we continue our repeated multiplication out. And our y-intercept, well, when x is 0, we have 0.81 to the 0, which is 1, times 5 is 5. So the y-intercept is 0.5. Same directions. Next function, y equals 21 times 0.3 to the x. Okay, so just by looking at this, we should notice we're going to have exponential decay. And now we have to figure out the percent. So we'll start by setting 1 plus r equal to 0.3. So subtract 1 on both sides, we have negative 0.7. So we see we have a negative r value. So we have 70% decay. And our y-intercept, when x is 0, 0.3 to the 0 is 1, times 21 is 21. So in this function, our values are decreasing by 70% over each interval, so as x goes up by 1, and our y-intercept is 0.21. Then we have y equals 4 times 1.92 to the x. So the base of our exponential function is equal to 1 plus r. So we subtract 1 from both sides, so r equals 0.92. So r is positive, so we have exponential growth. Again, we can see that in the original function. 0.92 as a percentage is 92%. And growth. And I should have specified this earlier. The way we convert the decimal to a percent is multiply by 100, in case that isn't clear. And our y-intercept, when x is 0, we have 1.92 to the 0, which is 1, times 4 is 4. So this function, we have exponential growth at a rate of 92%, and the y-intercept is 0.4. The function a of x equals 250 times 1.05 to the x can be used to calculate the amount of money in a savings account after x years. What does 250 represent in the context of this problem? So 250 is the coefficient of the exponential function, which we said is the y-intercept. Right? That would be the value we get if we plug in 0 for x. And we can check that pretty easily. 1.05 to the 0 is 1, times 250 would give us 250. So what does that mean if we're at year 0? That would be the initial amount of money that's being put into the savings account. So what does 250 represent in the context of this problem? We can say that it represents the initial amount of money. By what percent does the money in the account increase each year? Explain your reasoning. So first, looking at the base of the exponential function, 1.05 is greater than 1. So we do have exponential growth. Now the question is, how much greater than 1 is the base? So we could set up an equation, 1 plus r equals 1.05. Subtract 1 from both sides of the equation, so r would be equal to 0.05. Now this is the decimal equivalent of a percentage. We need a percent as an answer. So we have to take our decimal, multiply it by 100, and if we do that, we would get 5%. So the money is increasing by 5% each year. We're asked to explain our reasoning, so the simplest way is to say that the base is 0.05 greater than 1, which is 5%. How much money would be in the account after 8 years? So we're going to plug in 8 for x. So a of 8 equals 250 times 1.05 to the 8th. So we'll use our calculator here. So 250 times 1.05 in parentheses to the 8th. Hit enter. Now we're dealing with money, so we're going to round to the nearest hundredth, which would be the nearest cent. So that would be $369.36. So $369.36. That's how much we would have after 8 years in this particular savings account. Next question. Ricky purchased a new car. The value of the car can be modeled by V of t equals 20,000 times 0.9 to the t, where t is the number of years since purchase. What does 20,000 represent in the context of this problem? So again, 20,000 is the coefficient, so that's the y-intercept. Right? It's the value we would get from this function if we plug 0 in for t. And in the context of this problem, that value is the purchase price. It's how much Ricky bought the car for. Okay, so it's the purchase price of the car. Right? 0 years that he's owned it, so when he bought it, the car was worth $20,000. By what percent does the value of the car decrease each year? Explain your reasoning. So now, if we look at the base of this exponential function, it's less than 1. So we do have exponential decay, right? It's decreasing. Now the question is, how much lower than 1 is the base? So the equation 1 minus r equals 0.9. So we can subtract 1 from both sides of the equation. So we'd have negative r equals negative 0.1. And we can divide both sides of the equation by negative 1. So r equals 0.1. Again, we have a decimal equivalent, but we need a percent answer. So we need to multiply by 100, and we would get 10%. So the value of the car is decreasing by 10% each year. And our reasoning is the base is 0.1 less than 1, which is 10%. How much would the car be worth after 10 years? Okay, so we're going to plug in 10 for t. So V of 10 is 20,000 times 0.9 to the 10. Okay, so 20,000 times 0.9 to the 10th. Hit enter. Again, we're dealing with money, so we'll round to the nearest hundredth. So in this case, that's 6,973.57. So 6,973 point, just double checking there, 57. Okay, so that's how much his car would be worth after 10 years at this rate of decrease. Okay, so the main focus of this video was identifying whether an exponential function was exponential growth or exponential decay. We talked about the y-intercept, which is that coefficient value of the exponential function. And then we also worked at identifying what the growth or decay rate was. And that's all based on whether the base is greater than 1 or less than 1, and by how much. So now it's up to you to practice and feel confident with all of these before transitioning into our last video, which is on word problems where we're creating the equation on our own. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.